Jeremiah, yeah,
Yeah.
Jeremiah, sorry to intervene, but this is the signature of a Mach process. A Mach, Ernst Mach's, if you create like a warp drive, then if you elevate something by this warp drive, then it steals the energy from space-time. How does it do it? It pulls down space-time, so even very far bodies of mass are affected. So if the moon is above you, you should get like a different interaction comparing to a situation in which the moon is not above you. So this is actually a signature of either inertial dipole or a warp drive.
Well,
You should get different results when the moon is above or not.
the largest physical forces and bodies in our physical realm solar system are the planets and the sun and us on Earth.
Yes, of course. But
So
why would that apply to
gravity and
electrolysis?
magnetism interacting each other. The biggest forces is where they're positioned in regards to each other.
That's
Yeah,
true.
That's true, but why will that apply to electrolysis?
It affects the
What I'm
electron
saying is
spin.
that
And if you have separation, if you have charge separation, then you do get dipole, you do get inertial dipole. But you need like a huge charge separation with like a thousand PF picofarad of tantalum pentoxide, which is actually the best material because it has low relative permittivity. So you get less dipoles opposite to the field. So with tantalum pentoxide, and once area of 1 square centimeters of the plates and 10,000 volts, I did the calculation. You lose 3.6 multiply 10 to the power of minus 5 grams. That's the best. If you have like a material with relative permittivity of 4,700 or 4,000 actually 500, this is another type of high voltage capacitor, you get only 2 multiply 10 to the power of minus 7 grams. So the higher the permittivity, the lower is the effect, because what happens is that the dipoles inside are aligned opposite to the external field, and they cause an opposite inertial dipole. But that also calls for description of what charge does. So it's according to the geometric Chronon field theory, charge generates gravity also. It's 1 coulomb plus 1 coulomb generates 5.8 billion kilograms of gravitational mass, not inertial mass, and negative 1 coulomb generates 5.8 multiply 1 billion. So it's 5.8 billion minus 5.8 billion kilograms for an electron, for a negative charge. So this is something that is not known to concurrent physics, but just to explain to you why it's like that way, I need to show you like an introduction, to give you an introduction to.
Are you familiar with space warp dynamics? They have like microwave antennas that they interact with, and they try to like energize the air or whatever and create warp fields. Have you?
Is that David
Perez? Yeah, David Perez.
So what it does, what happens, because charge generates gravity much more than it should, then when you oscillate the charge, and especially when you have like spikes, you have like he has like fractal patterns. So it's at the edges of this metal, there is a high concentration of charge. So what happens if you oscillate it fast enough, you oscillate the charge fast enough, you get an effect which is called Harrow-Dwight warp drive. And this is exactly what he gets. And it causes like an asymmetry in the warp that he generates. So that's why he gets the effect that he gets actually.
Okay. Do you think it's possible with this technology to like move matter aside?
Yes, but you need to do some combination between charge separation and AC, like DC and AC. You need DC to separate charge.
Would you be able to say build a spaceship strong enough with strong enough field to split the sea and get the Jews out of Egypt?
Yeah, one possible. Well, with static electricity, it's going to be extremely difficult because you need the charge density of 10 to the power of minus 4 coulomb. Actually, it's 2 multiplied 10 to the power of minus 4 coulombs per centimeter square. This is a legendary charge density per area. So this is
It
extremely
was a
difficult.
teach once at a 3M plant in 1995, I think it was, or something like that. They had these massive rollers of plastic that were unrolling,
Yeah,
and lots of static was built up. And the way it was situated, it was sort of like a chet, like it went up and
yeah,
over.
yeah.
And in the center of that, there was a force field that if you threw anything against it, it would come back at you.
Well, I don't know if it's negative. If it's no, if it's positive, actually, it should happen, because like if you check the theory, then what happens is what causes actually the gravity. There is an acceleration field. That means that if you look at space-time and you look at what is called chronons, then these chronons are misaligned where you have matter. If these chronons are misaligned, which are also called causal sets, then a physical clock cannot follow a geodesic curve. That means there are forces or acceleration. So space-time gets angry and responds in an opposite way, which is actually what we see as gravity. And the cause is that there is an acceleration field that affects mass due to this misalignment of chronons, and you should get like repulsion from positive and attraction from negative, and the gravity is the opposite. You get anti-gravity from negative and gravity from positive. That's what happens. But the effect of the acceleration field is stronger. So in the middle of that cat, probably there was the cat was probably charged positive.
What was that word again? Chronon?
Chronon, yeah.
Chronon.
It's geometric chronon field theory.
Could I get you to
So
talk
a
a little bit
chronon,
about
a chronon is a quanta of time?
Yes, it's more than that. It's a wave function that sums to 1 on the entire spacetime. It's totally different than particles. Particles have their probability sums to 1 on a foliation of spacetime, actually in
So
space.
is chronon a measure of gravity then?
No, it's not a measure of gravity. It's a probability function that sums to 1 on spacetime, but actually you can multiply it with a unit of time, then you get the real meaning of it. So you can see spacetime is actually made
How
of
is it different than a
events.
Planck time? Okay, so it's much longer than the Planck time.
No, it's not. It's not
So
much longer than
a Planck time.
I'm trying to figure out what this is because the
Yeah.
Planck time's like the theoretically lowest, smallest interval of time. But this is the chronon set is a proposed quantum of time that is a discrete and indivisible unit of time as part of a hypothesis that proposes that time is not continuous.
Well, first of all, you don't have to assume the existence of chromons. You get them. You don't have to assume it. You get it from actually a theorem, which is called Geroch, G-E-R-O-C-H, Geroch splitting theorem, which says that in hyperbolic geometry, there must be a way to define a scalar field of time, not a coordinate. The coordinate of time requires also a direction in space-time.
So you said hyperbolic. Does that mean that a chronon is only emergent?
It is, no, it means that your space-time is causal. That's what it means.
Hey
But
guys,
then chronon, you're right. Then chronon is emergent. Then chronon is emergent, yes.
hey, I just want to say hi to Eytan. Is that how you say it? Eytan? Eytan?
Eytan.
Eytan. Okay,
yeah.
sorry about that. Thank you for joining us. He had some scheduling stuff, right? But he was able to make it. That's really, I'm really excited.
Thank
So
you.
I'm guessing Mark dragged you in, right? Or
Well, it was Tim actually, Tim and
oh, okay, yeah,
and
that
the
was
other
that.
guy, yeah, and the other guy, I forgot his name.
And Mark, yeah.
Yeah.
Okay. Yeah. Well, no, that's wonderful. Thank you for joining us. That's really exciting. I'm glad that we were able to.
Before you head out of
Did
there,
you
let me
miss
ask
the-
you about the acceleration field. Can I get you to talk a little bit more about the field of charged particle accelerations?
Yeah, let me share screen with you. Maybe I should share screen with you.
That'd be awesome. Could you? Yeah, this is like the big thing I've been on recently because I just recently comprehended it and we've been talking about it as a
Okay,
team. So the more we can
so
learn
I'm
about this, the better.
Oh, I
So-
just got a call from Flo Hardiman, which is Chris Hardiman's wife. And I'm going to go down there to Oklahoma to check out what he has left. He recently passed away while working on this
Wow.
this science.
Okay, so what you see here is called the Reeb vector, R-E-E-B. Reeb had a theory in 1948, and he invented a vector that measures how much a gradient of a scalar or a vector field, how much it changes in perpendicular to itself. And this is a measurement of how much a curve is not geodesic. If a curve changes in perpendicular to itself, it means that it's not a straight line. And in this time that it's we talk about straight lines in Minkowski geometry, in which the straight line is the longest and not the shortest, right? It's the longest proper time that you can measure between two events. It's counterintuitive because we are used to think about geodesic curves as the shortest curves, but in space-time it's the opposite, it's the longest curve. And you want to know how much this curve is non-geodesic. So what you see here is Z is actually the norm of P mu. So let's see, the definition of Z must appear in mono. Here it is. You have Z equals, the definition is P mu here between these two, between as and end. Yeah, Z equals P lambda. That is in tensor analysis. That means you take the square norm in Minkowski space-time. And you can actually define this vector, and this is actually not the Reeb vector. Half of it is the Reeb vector.
Can I ask you a question for clarification? Is
Yes.
the vector of the charged particle, or is the vector of a
No,
is it
no.
the vector of field?
We don't even talk. We don't even talk right now. We don't even talk about charge or electric field. We talk about what is a Reeb vector. We didn't even reach
Oh,
electromagnetism.
okay. Sorry, I'm not
So-
familiar with this at all, and I'm just barely capable of following you along with the mathematics because it's definitely not my strong suit. But I'm trying my best.
So this thing like half u mu, it's actually it's acceleration, because in 4 dimensions, if you talk about like a normalized vector in 4 dimensions, the vector that is perpendicular to it, it's the acceleration vector. It tells how much this how much this curve is changing in relation to the direction of the curve, how much change you have in a perpendicular direction. Now there is like a discussion and then the definition of the action of this Reeb vector, single Reeb vector, and then Einstein tensor. This is called calculus of variations. So you use calculus of variations, and here you get in 4. If you look at 4, there is a very strange result. You actually see 2 UK upper K and then you have semicolon lower k. This is divergence. This means divergence. This term means divergence. Now, since U is space-like and not time-like because it's perpendicular to a gradient of time, so it's space-like, that means that U looks like an electric field that has like something very close to 0 at the first place, and then you have EX, EY, EZ. So there is a further discussion that tells you that these terms like acceleration square divided with 8 pi k, which k is the Newton's constant of gravity, that's actually equals energy and density. There is discussion. There is a discussion that explains why it's like that, and why actually this acceleration divided by c square is this term here. You see what I marked here. Why the Reeb vector is actually equivalent to acceleration divided by c square, and you just go on with this development and you get something extremely surprising, that the charge divided by the square root of 16 pi, the gravitational constant of Newton and epsilon 0, that's the permittivity of vacuum. This is actually, it acts like mass, like gravitational mark. So 13 was a very, very surprising result, and for 3 years, I abandoned the theory because I said it's impossible. Simply
so
like
what
that.
you need then to fill this in, you have to get this effective relativistic mass that doesn't actually exist physically. This is a field. It's a mass that's effectively a field formed by charge Q. And okay, that pretty much answers like exactly what I was looking for on why the acceleration field creates the warp. It warps it as if it was a mass there, effectively, only because
right. But it's not exactly an inertial mass, because if you look at that field P mu, where do you have P mu to show you? I'll go backwards.
Because it's a directional vector, right? So it doesn't
Yeah,
really-
it's some sort, it's a gradient of a scalar. It's not even a preferable direction or anything, just a gradient of a scalar. And this gradient of a scalar doesn't have to coincide with speed because the charge can move in a different way. If you look
So
at,
is it just about the total acceleration, not necessarily about the velocity then, or what?
no, if you look, you want to describe a field of acceleration, a field that accelerates every velocity vector. So there is a way to do it by Skar and Friedman. Skar and Friedman, they published a paper, to the best of my knowledge, it was 2011 or maybe 2012. They published a paper that you can define a matrix, an anti-symmetric matrix, multiplied by velocity divided by c, and then you get the acceleration divided by c squared. And this is called acceleration matrix. They use it not for my purpose. They use it to define uniform acceleration. I use it in a very different way. I use it to describe a field actually. And this acceleration field is actually rotation by 90 degrees multiplied by a scaling factor in two different planes. In order to define acceleration, it's not enough to use one set of vectors, like something that behaves like velocity and something that behaves like acceleration. You need two planes in space-time. And
that makes sense, right? Because you have to have one vector has to represent your instantaneous velocity. The other vector has to represent your direction, right? And those two together equal your acceleration at any given point along this trajectory, right?
Right, and this looks exactly like it looks like exactly like an electromagnetic tensor, exactly like that. And you can actually complete it to two planes by using what is called the Levi-Civita tensor, not Levi-Civita symbol, but Levi-Civita tensor. It's a little different. So this is actually the theory behind it. And like there is a discussion about it and why it's like that, and the development of that. I also want to tell you guys that my wife is an active partner, but not in the theory that I present, but in another part of it, which is actually a patent application. Yeah, and she really supports me, and she's a smart woman.
Ethan, I remember your name, and I can't remember from where. Do you have other patents already?
Well, we submitted another one, and we'll see what will happen with the other one. So we submitted like 2 patent applications.
What's the name of one of them? I just want to see if you're the same guy I'm thinking.
It's 16/177/167.
16/177/167. You said
16/177/167.
177/167. Okay, look it up.
Yeah, and so this is what happens with the mass. But there is bad news for ceramic capacitors, and this is why the patent is needed. If you look at the ceramic capacitors, this is what you get. There's 3.6 multiplied by 10 to the power of -5 grams weight loss. That's not enough even to measure like with the most sensitive scales of what is the resolution of 0.1 milligram. That's not enough. That means it's really strong.
That explains why I haven't seen a darn thing, because I have never seen any force in that kind of a system with a static charge. So
yeah, it's extremely small, and this is the best case. If you use this is for the electric constant 25. If you use a higher dielectric constant, then it's going to be even weaker, like by 2 orders of magnitude less than that. So that is the best case, and it depends on the weight of the slab, the dielectric slab, and of course on the dielectric constant. And the higher the dielectric constant, the worse. It's the worse for the same charge density with the same. So actually, if you look at that, it actually means that it's impossible to do it with just static electricity and the ceramic capacitor. It will simply not work. It's even very difficult to measure this effect. So if there is a way, I wanted to show you what happens eventually. This theory, this is something from Seth Lloyd from MIT. And this theory reaches something very interesting. It reaches the probably the exact mass ratio between the muon and the electron. This is outrageous because the standard model has nothing to say about it. So you get a prediction. This is the prediction from of the muon's energy in mega electron volts, you get 105.6583745. I think that the current one is 55, not 45, but 55. But from 2014, it was 45 at the end. So if I look at the internet and I look let's look for that value, 105 point, what was the number there? I think it's 5, let's see, muon mass. 538 or something like that. 337 and then 45 MeV. I think we will find something, or maybe it's less. Okay, so I think it's less than that. What was then the paper? Because I did find the
Ratio was
exact
200, I thought, 200, a little more than 200.
Yeah, it's a little more than 200. That's exactly what I get. I get the exact number, but I don't remember. I don't remember the where I found it, but I found it in 2014. Muon mass. Let's look for it. Muon mass in MeV from 2014. That's all I find it. Let's see where it is. Okay, muon ping. Here it is. Let's look for that. I think it was, I don't exactly remember. I think it was 638 or 666 or 6, something like that. But this is what I got. I got the exact in 658. I'm sorry, 658. Let's look for it.
Are these papers available for download?
Not yet, because I want to submit it somewhere.
Okay.
Here it is. Here it is. We found it. We found, I think this, oops. I found the exact number. 105.6583745. I got 455 at the end.
Oh.
So that's very, I mean, the possibility that this thing is just by fluke of chance is almost zero. It's one in something like 10 billions or something like it.
Could I ask you another question about one of your patent applications? I'm just taking a look at like the 3 coils on this system, and I'm just curious to go over it real quickly, and if I understand how it works.
Mm-hmm.
It looks like you're directly connected across the center coil. You have a DC power supply, so that's just to set up a permanent magnetic field.
Yeah, what you need is actually a combination between AC and DC. The AC is in order to reach what is called the Harold-White effect, Harold-Sony-White effect. That means that by just simply by charge separation that we can achieve by DC today, it's what we get is not enough to get an inertial dipole that you push you upwards. Sorry. So that's why you need some AC component. This AC component is the same AC component that helps to get this thrust in the device of David Ferres, and also in other experiments like the experiment of Timir Data.
So the middle coil, then the middle coil is some kind of DC that's constant and it has an AC component on it. Is that right?
Yeah.
Oh, so basically it's a DC that fluctuates. Then it's a DC with a signal riding on top of it.
Yeah, on 2 plates. The best application is 2 plates and 2 plates, 2 plates below and 2 plates above. But you need very high power AC in order to soften. What you do is you soften the rigidity of space-time such that you will need a much weaker inertial dipole to get elevation, to get flight.
What kind of impulse powers are we talking about?
Thousands of watts. For a small device, it's even thousands of watts. So you need very powerful heat dissipation for it. So
it just seems so simple. Like this should be easily constructible with just a 2-phase system, right? And a transformer. Actually, your transfer
depends on what you want. It depends on how much power you want.
Enough to measure.
Enough to measure, then you get thousands of watts. Like between 1,000 and 2,000 watts, you need to get just something.
That's no problem, though. That's playing around power. That's nothing. Yeah. So I'm just kind of asking, like, if we pump 2,000 watts into a design like this, how physically large does it have to be before what does it have to be made like in order for us to see any kind of effects measurable?
A radius of 10 centimeters should be okay. Yeah.
Well, I might start building this thing tonight then.
Yeah, you'll get something measurable for sure. It will be sufficient for like I don't think that for flight, but for satellites, like pushing satellites, it should be enough. I wanted to show you another result here.
Okay.
This is the surprise. This is a huge surprise. When you go through the entire calculation, this is again that the ratios that I used before. You get the exact fine structure constant in 40 on the screen. That's also from electrogravity, the exact fine structure constant. There's nothing like it that you can get from the standard model or from quantum physics. And the reason is that quantum physics is based on particles, not on events. This theory is based on events. So this is a result. This is a very surprising result. This number here is from a polynomial. Well, it's a whole theory that that has to be explained just to make you understand what happens. But in very big words, what happens is around the negative charge, you have addition of area. That's a negative charge. Around the positive charge, you have subtraction of area. So because the gravity is different, you have anti-gravity around the negative charge and gravity around a positive charge, and energy generates only positive gravity. So the
You said energy generates only positive gravity, as in only attractive gravity.
Yeah.
Because it contains energy and it exists in some volume of space. Therefore, the only direction for dissipation is outwards away from its point, and the only direction of force is inwards towards the point of concentrated energy.
I'm sorry, I didn't understand your question.
I was saying, so basically, it just means it's only inwards when you have energy in a volume of space, because it's dissipating from that point, and it only is dissipative outwards.
You can look at it, if you look at the graviton theory, that's exactly what happens. So what happens is, if look at it like a negative charge has positive energy, and the positive charge has positive energy, but the charges that generate different gravities. Like the negative generates negative, and the positive generates positive. But all together they generate positive gravity. So
the positive gravity hyperbolic, and is the negative gravity parabolic?
How can I explain negative? It's a result. If I understand you correctly, the negative gravity comes out of the Euler-Lagrange equations of the action of the Rib vector.
So let me ask it a different way. If I throw a ball up in the air, it follows a parabola. It falls back down to Earth in a parabolic trajectory.
By the way, whether it's negative,
that's a negative. So that's what I'm calling negative gravity. On the other hand, hyperbolic, like a hyperbola, goes up, a parabola goes down.
Now, when we talk about,
I'm saying in a hyperbolic gravity.
No, not hyperbolic gravity.
Correct?
It's not hyperbolic gravity. It's hyperbolic geometry. It's something else. Don't mix between the two.
But the gravitational force is pushing as opposed to pulling.
No, negative. If you have something with negative mass, let's suppose that it's not just negative gravity. Something that has negative mass will fall exactly like positive mass. And this is a mistake that most people make. They don't understand that by Einstein's equation of motion of geodesics, both negative mass and positive mass will fall in a gravitational field.
I guess I'm misunderstanding I'm feeling confused about how negative and how you can have negative and positive gravity have the same force direction.
Well, they don't. The negative gravity will repel Earth. It will repel Earth a little bit, but it will fall on Earth. Is that, do you understand now?
I'm sorry, I feel.
No, for that, this is like classic physics. It's not even, it has nothing to do with my theory even. By classical physics, negative mass will fall exactly like positive mass. Why? Because space itself falls. Gravity is not a force.
I don't understand that. I'm sorry. I feel confused. I have an unmet need to understand how the trajectory would, so like for a rocket has positive, a pushing force in the form of the propellant, it has a positive force of gravity. Another example of positive force of gravity is a balloon. If you're sitting in the gondola of a balloon, the balloon is pulling you up because the space-time in the balloon has a different density, and that makes it lighter than the air around it.
That's true, but if you take Einstein's equations of motion, that means that a body follows a geodesic curve in spacetime, which is the longest proper time between two events. It doesn't make a difference if you put a negative sign or a positive sign in that equation. It will still follow the same geodesic curves. That means that in Schwarzschild geometry, both negative mass and positive mass will follow the same trajectories. And this is something that confuses most people. They think, if I have negative mass, the negative mass will shoot upwards. That's not true.
So when I think of negative mass, I think of, so what you're saying, so a balloon, isn't a balloon a form of negative mass?
If you had, no, it's not. But if you had if you have not a balloon, if you had like 1 kilogram of negative mass, it would still fall exactly like mass. But there is a trick that you can do.
So are you saying anti-gravity and gravity are the same because it's like antimatter? If you had some antimatter, if I had a chunk of antimatter, because it weighs the same thing, it would fall the same. Is that what you're saying?
Yes, yes.
Okay, so you're assuming that in our space-time that antimatter coexists with us?
And if you and not exactly, because charge is not exactly, charge can generate anti-gravity, but it's still matter. It's not anti-mass. It's not anti-mass. But what it means that if you have I have a plate of negative gravity, it would repel Earth a little bit, yes, but it would still fall on Earth. It wouldn't hover. But there is a trick you can do. If you have negative gravity and positive gravity, this is known in classical physics. Today it's already classical. This is known as inertial dipole. And not warp drive. It's not warp drive. It can be interpreted as warp drive. Warp drive has different geometric conditions of what is called the exterior curvature vector, that curvature tensor that was used by Alcubierre and Jose Notario and Eric Lenz and others. What happens is, suppose that you have a plate of negative gravity, and above it you have a plate of positive gravity. Then what happens, the negative gravity would repel upwards the plate of the positive gravity. Now the positive gravity would pull the plate of the negative gravity. So together, if the field is strong enough, they would shoot up. And that's the idea of using an inertial dipole. And this is not my invention. This idea has been around for, I think, since 1994, when Alcubierre spoke about warp drive, and people said, yeah, you can have something less than warp drive. You can have something which is just inertial dipole, and that's enough actually to fly. If you want gravitational flight, that's enough.
Well, I appreciate you sharing this. I'm curious if you have any experimental data to support the.
Actually, there is from H4D from Brazil, because they performed it's very easy to botch up this experiment, but they performed it correctly. I personally correspond with Elio Battista Porcelli from the H4D in Brazil, and you could look for it. It's I think even in the old paper that I published, electrogravity via geometric Chronon Field and on the origin of mass, you can already see, like in ResearchGate, you can see a reference to Porcelli's work.
If you have a link handy,
yeah, I'll try to get that.
Of any of this stuff, would you please put it in the chat? Just
yeah,
just in the chat, and then I can open it up.
I've got the link here on ResearchGate. I'll pop it on there in just a second.
Yeah.
Yeah. So that's cool. So don't Just keep going. No, you don't need to do that right this second.
Okay, I have another question for you, Eytan. I'm looking at the diagram again in your patent application drawing, and you have what looks like coils, or it looks like wire being used, but you have it split into several different segments or sections. And
Yes.
Could you explain why that is, and how many sections are needed?
You can do it with two, like for the upper plates and the lower plates, but if you want also to oscillate the middle to get a stronger Harold White effect, then you need to have like 3 different coils to do that. Like 2 of them have middle bifurcations and 2 do not have.
And I'm noticing in one of the other pictures too that you have this gear motor assembly with a universal joint in the middle. What's it rotating?
Rotating is what happens. Like any dynamic component that you can add to the field, adds softening of space-time. So rotation is one of them, and I can explain to you why, but that's a long explanation.
It's not necessary though for it to rotate.
No, it's cumbersome with the rotation. It's just I wanted to cover that too. Here I just sent you one link in the chat box.
Thanks.
Yeah. So
Which patent are we talking about?
16177167. This is, I just want to know in what page I have it. What?
Could you link that patent application too? Because I'm actually looking at not that same one.
Can you tell me what one you're looking at or link it?
Well, like
maybe you should share what you
better, because the one I have is kind of broken. It's not really it's not displaying correctly on the web page I'm looking at.
So I'm just looking at the. Never mind. I wanted to look where's the Porcelli experiment. So just download. But I think it's on one of the advanced pages there. You have just a little bit confused about this. And to see where it is. I'm looking about the paper to see where's the Porcelli citation. Where is it in the paper? So I'm not sure about that, but I will find it. The name of the laboratory is H4D from Brazil. And yeah, I found the paper. Elio Porcelli Battista.
Jeremiah, can you post the patent that you were looking at?
I'm still trying to find the darn thing. I can't.
Actually, Ron Kita found it. Here I found the experiment.
Ron Kita just emailed me actually. He's trying to get back into the. Let me email him back.
I'll look at that H4D. I have one here, but I think I have even more than that. I have it has like a modern one from year 2000. This is the old one that I found. I found from 2015, but Elio Porcelli has a new one, a new experiment from 2020, and that's the one that I want to find. Let's see which we have H4D. That paper, I must have it. He did an experiment with symmetrical capacitors. So I don't find it here in this paper that is specific that I have here. I don't find it yet, but I did mention. Wait a second. I know where it is. I know exactly where is the citation. Inward. Porcelli.
Eytan, are you on the East Coast? You're near New York, right?
I'm in Chicago.
Oh, okay, middle of the country.
Yeah, that's
next to Jeremiah, actually. Oh, close.
Okay, find it. Oh, I found where it is. Let's find.
I was looking out. I think that's your window in the back. I was trying to figure out what time it was. Maybe
no, I have this computer. I have a computer that is not even adjusted. I have something that is not even adjusted. My clock is not adjusted. Okay, I found it. Let's see how they get to your chat box. How do I see the chat box here? Something so simple, huh? How do you get to the chat box?
It's near it's right next to the share screen.
Not next to the shared screen. Okay, let's look for it.
The green.
Is it on view options or in the green one?
The green one says share screen, right to the left.
No, I don't. Now I see. Yeah, chat. Now I see it. Yeah. Okay.
Just click on that. Yeah.
So this is.
I'm
I
really
just
excited
posted.
that you guys were able to get together today. I think this is one of our best conferences ever. So Eytan, thank you for joining us.
I would totally agree, Tim. Totally agree with you on that.
Thank you.
It's when you get diversity of ideas together, that's when things just blossom, and that's really exciting.
I particularly am very excited to have Eytan. He's the only other Hebrew speaker in this field that I know of.
תודה רבה.
בבקשה. גרתי בארץ 7 שנים ברוב היהודי.
Well, no, you have Jack. You have Jack. Don't forget about Jack.
He doesn't speak Hebrew.
Jack Safati, to my opinion, is not normal. I'm sorry, but this is my opinion.
He knows how to swear in Hebrew and insult you.
It's true, and it's not my. I don't have the energy for this.
Oh, he's fun in small doses.
He has his moments. When he came to the conference, that was terrifying and yet incredibly funny. So
Hector Serrano was like coughing on his beer, laughing so much.
Yeah.
Yeah, that's what we have to say.
I
want to see that
that article, by the way, the one that you linked the title to. I can't find it online. It's not a link. It's just.
Well, just look for keywords. Do you want you mean the experimental verification of
I searched the
anomalous?
DOI number. I can't find the DOI number. Which should be like the way to find it, right?
Maybe I made a mistake in that, but just do like an approximate search for it.
I'm just going to type in, okay, let's just go with experimental verification of anomalous forces on shielded symmetrical
capacitors, March 2020.
If that doesn't get it alone, then I just don't know.
No, you can see it in ResearchGate.
Oh, there we go. Yep, they finally found it. Thank you. That was helpful.
It did a very good job, not like the failed job of Martin Tamar, which totally flunked this.
Thank you for calling it out, because I was thinking the same thing. So many improper things and unanswered questions that just crush me, because it's not like I claim to be an expert on it, but at least I can read the inventor's papers and know that it didn't agree with those. So
Martin Tamar has a knack for doing something 99% of the way and then claiming that it doesn't work. Well, without telling everyone that
99%, that's a lot of credit.
Well, he knows which 1% to leave out that would make it not work.
That's true.
Like the batteries. There's no batteries.
Yeah. Well, I don't know.
It just
the batteries in there with this.
It sat there. Nothing happened.
Hey man, superconductor experiments, everything except for the liquid nitrogen.
Exotic light bulb.
No,
Robert Scheuer's the
Quark couldn't have been that important, guys. Come on.
I don't like to pick on Martin. No, I don't like to pick up. But what I would like is I feel like Martin probably has a few ideas that he'd like to pursue. Again, he's juggling a lot, right? And I would love to learn more about what he'd like to do in the future. Instead of replicating other experiments, what would he like to shoot towards himself? That would be really exciting. But I think he hasn't responded to any of my emails, so he's probably in hiding right now.
I heard from some people, I'm not gonna name names, but you all know who she is. that he is straight up paid to throw dirt on any good idea in this field. Yeah.
Don't you think that the worst problem today is the mainstream physics? That they're the greatest obstacle we have today.
I'm not a physicist. I haven't done any physics I was never wonderful at the math. I haven't done any in 12 years now or something. So that's why, I don't know. But I can tell you in terms of where things are going with dark matter and dark energy and things like that, I don't feel confident in mainstream physics like I used to. And I think most people feel like that in one way or another. But then for me, there are a bunch of questions. Like, for instance, I've seen a couple of different things, that portable neutrino detector. And then there's a company in Eastern Europe that wants to use that same idea, more or less, to try and create a battery, which I thought was really interesting if neutrinos are real. But then I have this question of, are neutrinos actually real, right? I mean, which sounds, I don't know, you know, I know I sound ignorant saying that, but like a lot of these things that have been proven, I'm not sure how proven they are, you know?
That's well, man,
Skepticism is a great thing. Don't underestimate the power of skepticism. And because, you know, you can think you have all the answers, but it's not, it doesn't work out. You're right, you know.
You know, true. But you know, if I could share something, this has been, for me, this has been because I've been covering this stuff for like a very long time, right? And I know you guys have all been in this. I think one of the biggest things that I've learned is never take the position that I am right. Because what I found is there have been so many different times where I've said to myself, there's no way, you know, this has to work like this, or there's no way this other thing could work like this. And then some new piece of information comes out and it's like it shines a different light on the same thing. And I'm like, no, I see how that could work. And so in some ways that probably makes me bad, because like, I don't like to take firm positions on a lot of this stuff. But part of that is because I just feel like I felt like I've been mistaken so many times in the past that, you know, it's kind of like, okay. And so I like to leave things to people who are smarter than myself. And it's like, well, he's got a good idea, just point him that way, you know?
Have you ever got something where you figured it out, but it was just, turned out it was just totally backwards? Seriously, have you ever had that happen to you where, well, you thought it was this direction, but actually it was going the opposite direction when the data came back?
There's been a lot of stuff like that. Or I will hear about an idea and the way that it's explained to me, I'm just like, there's no way that could possibly be. And then I'll meet somebody else who will explain the same idea a different way. And I'll be like, oh yeah, that makes sense. You know, but then I'm like, okay, what has changed? What's changed is me. So I shouldn't take really firm positions because I could be completely wrong, you know?
And that is a very healthy way to see things. That should tell you this theory of Chronon Field at the beginning was totally wrong. It started in 2003, and I had some ideas that totally did not work and were proven to be wrong. But that actually helped me to reach a different way. And actually, one of the breakthroughs came from Dr. Sam Vaknin, who is both a doctor of theoretical physics and a psychologist. He's a doctor of psychology, so it's a weird bird. He has 185 IQ. And he's the one who came up with the idea that space-time has two layers, the observer space-time and the realization of space-time, the collapse of events. So when a chronon dies, a reality is born, because you can only reach a place in space-time in which you have a collapse of a chronon. So what is the manifold of space-time? The observer. We don't know. Maybe it's not physical, because the physical world only has probabilistic events, and this observer space-time is deterministic. It's not the probabilistic. So the real events are these chronons, these probabilistic events, and every probabilistic system has a deterministic reference. You can say something like that. It's a little bit, by the way, it's a little bit contrary to the point of view of causal sets. They say, no, you have only the causal sets and that's it. But then you have a problem, because the Gaussian, it lives in deterministic coordinates, right? You can talk about the dice only if you throw it many times. So in relation to yourself, you're deterministic and you're the observer, and the dice is not deterministic. So this idea of space-time and space-time which is not physical, and space-time which is physical, in which all these probabilistic events happen, this idea is actually stems from doctorate dissertation of Sam Vaknin from 1982, but unfortunately nobody took him seriously. I did. I did take his work very seriously.
It's interesting that you mentioned psychology also, and for me, my ex-wife had a master's plus 90 in psychology and education, and I helped her study for the whole. I helped her study for all of her degrees, and I remember when I helped her when we first, when she chose that degree and started going that direction, I used to make fun of her because, I was more interested in hard sciences, and that's the exact opposite of hard science. But I've come to appreciate it. I've come to appreciate psychology in the sciences, because we interpret everything that we see through the lens of humanity, right? So
We're meaning-making machines in a meaningless world.
Oh,
That's from Landmark, the Landmark Forum.
I'm just looking at Esoteric Gold's outdoor, looks like a patio view.
Yeah, there's like some really crazy stuff over here. We got the Bernie dude with like his pickled aliens. Eytan,
The alchemist in the chat would be definitely some of the most interesting visual environments here.
Eytan, this is the laboratory where
yeah,
we're
yeah.
doing the experiment.
Wow.
Yeah, we got some serious stuff over here. Have you ever heard of the Alzaphon experiment?
No.
Basically,
I think I did actually once, but I got it through email, but I didn't understand what it is, so I can say no.
It's supposedly a way to make mass not interact with gravity and inertia. And it involves a laminar magnetic field, which we're producing using this electromagnet over here. It weighs like a ton. It's massive electromagnet. And
How
then
many Tesla is your magnet, Mark?
it's electromagnet. So I think it'll probably saturate at around 3 Tesla. But we're not
pretty good.
I haven't pushed it past 1 because that's all my power supply can push.
And what do you get? What are the findings?
Well, we're still in the process of building all of the parts. I have done it with a much smaller setup in the past that wasn't as laminar. We got a 17.8% weight loss, which was in the noise
That's
range.
a lot. Yeah, but that's a lot.
But there was a lot of noise too, because the microwaves were affecting the scale, and we shielded it, and there was still a little noise. I think there was a result there, but it was.
You never know.
It was a little too noisy, and the electromagnet that we built, that we spent a lot of time building, it wasn't laminar enough, because this is like NMR, EPR kind of stuff where you need very laminar magnetic fields, like very homogeneous magnetic fields, and that's what this thing is going to provide us. Now we're going to basically align the valence electrons in a sample using the electromagnet. Then we're going to hit the valence electrons at the Larmor frequency, which is dependent on the strength of the magnetic field at 28.025 gigahertz per Tesla. So that's way up in the microwave range. And we have 2 different setups for microwaves. So this is the signal generator. That's a signal analyzer. Down there is a 5,000 volt power supply, which is going to be powering this klystron over here. It's a C-band klystron. And it goes to a cross guide. This is going to tell us when it's when the chamber at the end is in tune, and then there's some isolators to keep all the power going in one way. So right now what I'm building is the part that goes on the end over here, the chamber where the sample sits in, and I need to make sure that it's perfectly in tune with the microwave. So there's going to be parts that can move in and out, and we're going to be 3D printing parts of the enclosure, like I have.
So the particles that you use, how do they use? They are just accelerated by an electric potential, and then what happens?
Well, it's basically just microwaves and magnetism. It's all. So
you have nothing else. You don't have particles that move inside.
No,
for photons, only photons.
Yeah, there's our electrons. Yeah, that's all. That's all that's involved, and it would also explain why flying saucers are shaped like flying saucers, because this is not the way you would actually build a craft. You'd have an electromagnet around the periphery of the craft, then have the shell of the craft follow the homogeneous field line, and that would be pretty much the shape of a flying saucer, which you have up over here.
How about counter-rotating coils like in the Glocke?
Counter-rotating coils in the Glocke. You mean
With the
spinning
current at the
coil?
same, the current is in the same direction. If
Mhm.
it's clockwise here, then the current has to be clockwise here.
Yeah, well,
But they're also-
I think he's talking about easy Elzaphan.
no, he's talking about the Nazi bell, Doug Locke,
Yeah.
the Nazi bell.
I know, but easy Elzaphan has a spinning disk inside of a magnetic field.
But you have, you know what it does. When you look at the current, if the current moves, you have like, suppose, let's use the terminology for current opposite than what is used today. Like, let's say that the current is with the electrons, not as it is used today in electronics. So it's the opposite. So if the coil moves like that, the coil rolls, and the electrons move to that direction, then the electrons will be faster here. You have the same motion for electrons, but this coil moves to that direction. So the electrons in this coil will move faster than in this coil. So what you see in the middle, a charge will see an electric field. Is that correct? Even a non-moving charge, right? Like a
You're talking
stationary.
about relativistic effects of electrons. It's basically you're pushing against space-time and creating a thruster.
Thruster.
And Richard Van Durk is working on something similar, and so is Jeremiah. Those are all thruster devices. This is something that will make things weightless and allow you, with the addition of a thrusting device like you just described, or like an MHD or just a regular rocket. And as Frederick Elzaphan explained, like once you achieve, close enough to 100% weight loss, you can make it to the moon with a can of hairspray. Like,
that's true.
Yeah. And one other thing, Einstein said nothing can travel faster than the speed of light. Now let me reword that. The only thing that can travel faster than the speed of light is nothing. So if you make the craft weigh nothing, you can travel faster than the speed of light.
That's true. Actually,
So-
space-time itself moves. That's a different story.
That's
So it-
warp drive, and that's another a
Yeah.
whole nother sugya. But actually, there's a lot of different theories about why this experiment will work and if it will work. And we're trying it with two different frequencies. We got the C band, which is in around 6 gigahertz. We also have the X band, which is like 8 to 12 gigahertz. And I literally just got parts in last night I have to take them off the board to build the chambers and stuff. And so yeah, we've been doing a lot of experiments here, not just Elzaphan. We also did the Podklanov impulse experiment. We did that twice with
What is that?
it's where you're impulsing power, a whole bunch of power into two superconducting disks that are inside a magnetic field, and it's supposed to create a gravity ray gun sort of thing.
Well, if you read the paper of Harold White, you see that you need like at least something like 10 gigahertz, at least, to be able to use less than like 700 kilograms of negative gravity. So you should actually use, to my humble opinion, you should use very high frequencies, high RF frequencies.
I mean, we have the ability to do 10 gigahertz. It's not a problem. But what are we doing with the 10 gigahertz?
In terms of the Podklanov discharge impulse thing, let me explain real quick. So we're not worried about frequency because it's a singular event, and the event is designed to be as fast as possible by any means to the discharge. So we're achieving that with the Marx generator. That gets us up to about 900 something thousand volts or more. So that's our impulse discharge, and because it's a ultra fast rise time event, it effectively gives us a remarkably high effective frequency that's probably well into the
So you use spikes, actually. You get spikes.
Right, it's just a single spike, just a single discharge event straight into the thing. And so electrons will rush in to the superconductor. They will tunnel through it and go again in almost instantaneous acceleration as a result of their flow through it. And when they exit it, they'll have forward velocity and that acceleration. The superconductor won't be able to hold them back. They'll experience no eddies by trying to move away. So they'll just simply take all that forward momentum and fly straight off the surface in one huge clump. And because they're already Cooper paired, basically they're going to stay inside the vacuum, and they're going to have all this momentum in one huge clump, and they're going to arrive at the target all together. And suddenly, during that entire time that they're accelerating, they're going to arrive at the target and lose all their acceleration by crashing into it, but all of their forward momentum, that compression field created by their acceleration because they're electrically charged particles, particles, it still should travel straight up through the target electrode forward, and that's what he was reporting as a beam that could travel through almost anything. And it was a a voltage differential change that could divert a laser beam and could push on any object of any material.
You just gave me an idea. If you have like two disks, each one of them is a superconductor, like in with liquid nitrogen, and you assemble them exactly like the Glocke, like the Nazi build. You have one rotating clockwise, the other one rotating counterclockwise, like that. And there is a hole in the middle of them, and you have like a coil, and you change the magnetic flux through the coil. So you have like with a huge spike. So you get like a huge spike of how do you call it? Of electro. How do you say it in English? I know it in Hebrew.
How does it say it in Hebrew?
כוח אלקטרומניע.
A back EMF spike?
Yeah.
Electromagnetic.
Wait a minute. Hebrew has a name.
Mania
for back
means
EMF?
start. Electro starting.
Are you
So never
talking
mind.
Are you talking about the precession or the not the precession, the helical motion of the electrons
So
down?
if you just change the flux of a magnetic field through a loop, you get current, right? So you have some voltage in it. So that's what I mean. So you have like a coil in the middle. Then you use like a huge spike, or you have like a high current. Then you open the circuit, so you get a huge spike. So you get a huge spike into these superconducting disks. Each one of them rotates to a different direction. Then you will probably get something much stronger than in the Nazi build. You get an effect which is much stronger. And I wonder why this experiment was never performed.
Probably because rotating superconductors just to begin with is already, practically a feat of magic.
Well, 1 second. Isn't Wayne about to do that? And I just got some.
I didn't say Wayne wasn't a magician, Mark.
Okay. Yeah, we deal with lots of magicians.
Yeah.
Actually, Jeremiah over here has a Harry Potter wand.
It's
Working.
It's not the Harry Potter one.
It looks exactly like a Harry Potter wand. Here, pull it out.
That's trademarked, and you can't use that. Again, it's not. You're not associated with the.
Okay. It's the electric magic wand.
It's very simple. It's a generic name that is totally not trademarked by anybody.
Okay.
Yeah,
By the way, Eytan, I think that word is electrical
seen
impulse.
this.
Electric impulse.
Yeah. You're talking about cutting off a coil's circuit, so then there's a spark.
Not only if you change the magnetic flux through a loop, you get like you get force exerted on each charge, right? So that's what
Yeah,
I'm
and then
talking
that
about.
builds up, and then you get the spark gap, and that's how an engine fires. Like
Okay.
that's what happens in an engine too.
Yeah.
With a coil system. Yeah. It's an impulse.
So you can get like a very high impulse of like temporarily very high current in these counter-rotating disks that you mechanically counter-rotate them. And
We're actually doing something like that. I built a coil. Jeremy came down and helped me with that.
Yeah.
And I got a massive vacuum chamber over here for it because we're going to cover this with epoxy and put like 35,000 volts across it with a spark gap. So have it pulsing back and forth, and we're gonna have a disk spinning in the center to see if that creates that
okay.
dynamic nuclear orientation effect. Similar to what
Okay.
we're doing over there. There's supposed to be several ways to achieve the effect. Yeah, we got lots of crazy science experiments. Do you ever come around to New York City area?
I've been, but to the Rebbe, if you know, it's 770 Brooklyn. Fahrenheit.
Oh, at the Chabadnik.
Yeah.
Okay.
Try to.
Okay, very cool. Yeah, they. I had some Chabadniks that tried to get me back on the path, and I challenged them, and then they got scared of me.
Oh, I was an eccentric Chabadnik because when I was in Israel, I used to leave water and Tupperwares for the cats, for the street cats, and for hedgehogs, because in the summer you don't have rain like for several months. So most of Chabadniks, they do not do these things. Some of them do. Some of them do leave water, but they don't leave like in certain like places.
I think that's really
I was in-
thoughtful. I think
I
that's a
was in
really
a
thoughtful
car
thing to
pod.
do.
Yeah, that's what I did.
I got lessons on the flute from Avi Piamenta.
I know who is that. Yeah, I know this guy. Yeah.
Yeah.
So that's the only knowledge I have of New York. So what do you want to say about New York?
The lab is here in to northern New Jersey, so you can come down and visit if you want to see some experiments live.
I hope that everything will be arranged with my immigration here, because they give me a very hard time. I'm married to an American woman, and they give me a very hard time. Like for 3 years, I don't have a green card already. Yeah.
I mean, you could fly or you can drive here. I mean, we're
Mm.
kind of far, but to drive. I think it's like Chicago to New Jersey is what, like 10 hours
10 hours that's a lot. Yeah.
or 7 hours or something like that. It's a long drive, but it's doable.
Yeah.
Hey, Ethan, you're located where?
He's in
In
Chicago.
Sauganash, north to Chicago.
Really?
He,
Want to
Jeremiah,
hang out and build your drive?
What?
I said, do you want to hang out and build your drive sometime?
Well, it's first of all, it belongs both to me and to my wife, so she has to agree.
Do you both want to hang out and build your joint drive sometime? I'm just in Milwaukee. We're not that far away, you know?
Yeah, you're not.
if you
Milwaukee
want
is
to, I'll
Wisconsin.
fly in. I'll fly in to Milwaukee to see that.
Yeah, I'm
Yeah.
just saying, like, it could be a heck of a collab. We could actually build it.
Yeah.
I would love to build that tank thing. That's really cool, man.
Yeah,
I think I understand the principle. I don't totally understand the arrangement of the parts that you have, but that could be fixed with some better diagrams, which we'd have to draw anyways. And it's like the idea is pretty implementable. It shouldn't be impossibly high frequencies that we need, right?
No, it's like if you have between 10 to 30 gigahertz, it should work, and you just need high power. You need the only thing you need high voltage for is because you have like a bad capacitor. You need a lot of voltage for it, but maybe there's a way to overcome it. Maybe we can.
Can we exchange frequency for voltage? Because it's going to be very, very hard to generate that power threshold. If you looked at the semiconductor industry for gigahertz range output devices, you'll find a major cutoff point right around the 2.4 gigahertz to 3 gigahertz range at 2 watts, and then it's just going down to the milliwatts or about 900 milliwatts max frequencies above that. And that is not into the power range that we're going to need. So what we can do as a supplement is we can go into the into the high megahertz range, or even the
No, megahertz will not work. Megahertz is not according to Harold White.
Even at say like 30 or so thousand volts.
No, you need. This will work with like something like 140,000 volts DC and something like 10 gigahertz at between 1 kilowatts to 2 kilowatts. That's what we
That's
need
an
for it.
impossibly high frequency at that voltage, though. How in the world are we going
No,
to?
no. The DC is
No, he's
one,
saying DC.
the DC is 140 kilovolts. The
Oh,
DC, not the AC, not the AC.
How high does the AC need to
Eytan,
be?
what I have in the lab right now, the Klystron is capable of putting out 3,500 watts, and I have 125 kilovolt power supply DC.
That's fantastic. Then it's doable. Yeah.
Okay, so come down to New Jersey. Let's do it.
Let me just clarify real quick with this, Eytan. So you've got the high.
I also have a Faraday cage too. That's big enough to stand in.
In this case, by the way, the DC is just to introduce asymmetry in the field, because the DC is not sufficient for producing a viable warp
So
drive.
what I'm asking is, like, when you put in this high power, you need some reasonably high power in the gigahertz range. So could we use like maybe could we acquire an old cell tower repeater, for example, like one of those transceivers?
I don't know what is that. I know that I have a friend. I have a friend in Israel who is an expert in RF. His name is Elad Dayan, who builds these things.
The towers that
I want to
they
speak to
have
him.
really high power microwave equipment on them, 5 to 10,000 watt boxes that will, that.
What was his name?
His name is Elad Dayan.
Elad Dayan?
Dayan. He works in Siklu. He works in a company called Siklu. And what they do is they build a radar for like anti-terrorism. You put like some device on the wall and you see what happens behind that wall. It reflects like the images of the people.
Oh yeah, Siklu. Here it is. Yeah, I found him. Elad Dayan.
Yeah.
You know
So
him?
he.
Oh yeah, I need to speak to this guy.
He's a guy that has a capability.
Why are all the smart people in Israel?
No, not only. Yeah, but I think actually the highest IQ tests the average in the world is Japan. It's not Israel.
But whenever I'm buying like stuff for the lab, there's an inordinate amount of stuff that is coming
But
from Israel.
wait a minute. We don't have anybody from Japan. That means they won't have anything to do
Well,
with us.
Will is in Japan right now.
Oh, that's true. That's true.
He's in Japan, but he's not Japanese.
Exactly. Does that mean that we're on the wrong path and we're screwed? Like they won't have anything to do with us. The world's smartest people are like, no way.
Well,
The
Americans
smartest
are.
people on the planet are actually the Japanese. I have no doubt about it.
No,
Haven't
I'm
helped
just
you.
teasing, guys. I'm just being a smart ass. It's that time of the night.
It is pretty late. We've gone for an amazingly long time, but I don't think we're done yet. People
Well,
aren't-
you're blocked, Will. You got to unmute yourself.
Sorry, I'm still here. I'm just listening.
Are you-
Will's been up for 36 hours straight now.
Yeah.
He's only hallucinating a little bit. He's looking at the wallpaper, wander across, right? Because it's like what time is it now? It's like 1 PM in Japan, right?
What 1:30? Yes. in the
Uh,
afternoon.
Tim, did you get a hold of Takaki Musha from Japan?
No.
You know, he did an experiment opposite of what I say. The top was plus and the bottom and the sides were negative. So that actually causes a thrust downwards, but a very weak thrust. Like his capacity was really, really bad. So this effect of dipoles, inertial dipole is almost zero. But what he did, he used AC, and he didn't use high frequency AC, but he used very high spikes through like, I think it was rectangular waveform.
Oh, okay.
And he got weight loss because in his configuration, if you analyze it and take my theory in his configuration, you understand that the AC is much more dominant than the DC. So even if it doesn't make a difference if you use like negative on the bottom, plus on the top, or the opposite, it doesn't make a lot of a difference. What does make a difference is the shape, the waveform of the AC that he used, and he succeeded to achieve weight loss, and it was replicated by J.L. Nodin from France.
Yeah. I know Nadan did a bunch of, and part of that's he kept doing experiments after I kind of got out of this, but I know he's done a bunch of additional experiments. So, and I think even Nadan got out of this after a while, didn't he? I think he slowed down several years ago. Maybe not. I would love to have Nadan on I would love to have him on APEC.
Yeah, you're not going to get him, I don't think. Last time I checked, he had finally gotten to the point of developing and getting his own patent, and it was for an energy generator. And shortly after that, he went overseas. He went to one country, and then I think he ended up going to a second country now. I think he might actually be in Japan right now, or one of the somewhere out there in the Asian area. And anyways, like I don't know why he got out of Dodge, but my guess is it has everything to do with his last invention that he patented, which was effectively a free energy generator that apparently used plasma to act as a charge separator, the natural collapsing of plasma to carry electrons with it, and consequently generated significantly higher voltages with the same quantity of charges, therefore extra power output. So I don't know if he got out of Dodge because of that reason, but I would not doubt it. And then since then we've heard nothing from him.
Well, but I think the other thing is I'm not sure if I've ever heard him speak either. He might not communicate well in English, right? He was in France.
He speaks in his videos on his website.
Does he?
Yeah.
Okay. It's been a long time. So
he has a very strong accent, but it's easy to understand him because he slows down his words and enunciates each one clearly, because he knows he has the accent that he wants people to understand him. He's quite, wise and very self-aware of that. So.
Oh, well, that's awesome. Yeah. Well, yeah, if, I could try and reach back out, but that does happen, right? People get involved with projects, they get pulled away. Mark is laughing at me.
I'm not laughing at you. It's crazy what's going on here. Esoteric Gold. It looks like he's a freaking alchemist. I don't know.
Dude, Esoteric Gold is literally an alchemist. That's what he does. He is literally an alchemist.
And then we have like pickled aliens over here.
Wait, your screen is different than mine. Oh, that's because you're the host. You're the host. Let me see.
Go to a gallery view.
Oh, okay. No, I you know what? Well, I'm still recording, so I know.
Which is excellent. This is a very good session, that's for sure.
There we go. Okay, we'll go to gallery view.
Yeah, go to gallery view and just see what the hell's going on here.
Well, we have a lightning Heineken.
Heineken is great beer.
And we have pickled aliens over here that he's adjusting the light on.
Oh, I see. Yeah.
And esoteric gold has like the lights going on in the background while he's trying to turn mercury into gold.
Well,
Probably it will be radioactive then.
Yeah, well,
that'll work.
he's counted on phlogiston.
Mhm.
Well, one of the interesting things about Isaac Newton and his esoteric papers is that Isaac Newton stated that the Rosetta Stone should have enough energy that you would have to have protection to be around it, or it would actually kill you.
Like the Ark of the Covenant.
Now, what's interesting about that is we know that when we take lead and we put it in a nuclear reactor with uranium, a uranium reactor, that the uranium reactor after several days will produce gold from lead. It will literally
Radioactive gold.
Yeah, it's probably true. Yeah.
And but the only downside of that is now your gold's radioactive.
Yeah, only. Yeah, sure. Wow, that was actually
It's hot.
expected.
You call it hot
So-
gold.
So it's interesting that Newton was smart enough to know, what it would actually take, or what it could take.
Yeah.
What it could take is a better way to say it. To translate lead into gold.
No, you can't translate lead into gold. They can do mercury into gold or platinum into gold.
They used the projection power is what they did, but that's a whole long discussion. So
I read somewhere that in the Vimonocraft, they have problems where the mercury turns into gold and it clogs up the pipes.
I hate
That's a
that.
problem.
And then they have to scrub out the gold and throw it away. They're like, God,
Yeah.
Yeah.
get rid of this.
No, we
You
don't
know?
want to go.
Yeah.
It's crap.
Not
Yeah.
that janitor's job.
It's clogged up with gold again. Okay, send it to the cleaners.
Oh.
all
By the
those
way, you
technologies
mentioned, yeah.
have to
you-
do with monatomic elements. So anyway,
Yeah, because they're spinning it around so much that it loses a neutron and it becomes gold.
yeah, they also said that it tasted sweet like honey, which is also on the same level as the bread of life, which the pharaohs partook of. So
Well,
yeah, there's so many similar things.
there's some interesting. I did a story on Proton 21, which was and actually they are working. I think they're doing contract work for Los Alamos now, and I forgot the guy's name, but they had some really interesting stuff too. They were doing pulsed. What would they do? They would take these copper electrodes and then hit them with like a multi-megawatt, multi-gigawatt, like a Marx generator pulse, right? Super high energy pulse. And these things would explode and deform, but they believed that they found basically kind of like this pulse, low energy nuclear fusion, right? They were doing transmutation with these. And they found some really interesting stuff too. Energy levels that were way below what fusion should happen at. So, and they did a bunch of papers on this. This was like the 2004, 2008, around there.
I read somewhere about the fusion bombs that in one of the tests by Russia, they found the explosion was a lot more powerful than they expected, and then they discovered later that there are certain fusion reactions above helium that don't take as much energy as hydrogen to helium.
One other thing just
So
popped into my head.
Like a layering material of the bomb became fused with something else and became a new.
I also heard that it was the time of year where our alignment to the sun and planets brought in more energy and also determined the nuclear yields of these bombs. And they did find out that if they did it at the same time on the calendar the next year, that it would also come up with the same yields. So anyway.
So another thing that I was going to mention, this just came to mind, was this proton 21 thing. They found an anomaly when they were doing their pulsed work. They had what they just called it a black spot, and they were using an electron beam and a proton beam to basically map these elements, right? That was how they were doing their spectroscopy. This black spot, what they found was they had no signature. It was like it just basically the beam disappeared into this spot. It was tiny. I think it was like 10 or 20 atoms wide or something like that. But the thing that amazed them was they were saying they would focus this beam on it and just pump energy into it, right? It's like a probe beam, and they would get nothing back. And so they documented it and basically just moved on after that. They had no idea what it was.
Well, that was a mistake, because if you have like a boundary of a hole in space, you have like a ring of negative and a ring of positive in a certain way, then you get a wormhole, and that can be proven. If you join my theory to this, and you just join the fact that you know that negative charge can cause negative gravity, then it's only a matter of some mathematical manipulations to get a wormhole.
But it could be. What they described was, so again, and I could try and find it for you. In fact, I'll try and find the article, because I had pictures of some of it. But what they described was they were taking these copper electrodes and hitting them with these super high energy pulses and picking up these different transmutations. And then this black spot, and I believe they said they saw this once, maybe twice, but the thing that got them was that they said using these beams, they could just pump energy in again and again, and just kept sending energy into it, and it just disappeared. And I had wondered if maybe, I don't know how, but like maybe they created neutronium or something, but the energy levels for that are so much higher than,
I think the secret has to do with isotope, because they have more neutrons. And if you think about it, if it's full of neutrons, then it's gonna sort of have fuel, and they're basically gonna push outward its subtle energy, sort of wear the neutrons themselves down as they pass that energy on outward through the electrons and protons. My belief is that neutrons are pretty much where it's at. That's why if you look online, there are so many neutron devices, and anywhere from giant lab neutron devices to handheld neutron devices there's tons of them out there that they're selling. I'm just curious why, Anyway.
Neutrons aren't stable though. If there is no free neutron, it decays into a proton, electron, and a neutrino, essentially.
Supposedly monatomic elements soak up neutrons and energy like thousands of times faster than normal matter, but it also can release energy thousands of times faster. So that's just all this literature that I've read from David Hudson and stuff. It's pretty interesting, but I have to get my notes together so I can sort of have the information right in front of me. So
cool.
Anything that should be said here is about this idea of free energy. So if you get energy out of nowhere, it's on expense of something, and most likely that you actually interact with far bodies of mass. So if you create like an electrogravitational effect, you create gravity.
Energy's been around for over 100 years. It's called solar panels.
What are you talking about when you say free? Are you talking about vacuum energy, or the so-called the simultaneous creation of antiparticles? And
the same. If you get more energy than you invested, and you don't see that this energy enters through like solar panels or through known forms of energy, through particles, radio waves, even like gravitational waves, any like known form of energy, then most likely that what you succeeded to create some sort of a gravitational field, and you stole energy from space-time by pulling far bodies of mass a little bit closer to you by, let's say, a nanometer or even less than that. But that is known as the Mach effect. And there is a nice paper, actually two nice papers, Dennis, I think it's Sciama. How do you spell it in English? Sciama.
Sciama. Actually, I don't think I pronounced that right either, but I believe it's pronounced Sciama. Dennis
Sciama.
Sciama. And I don't remember who's mentioned that. I've heard 2 or 3 people mention that name. That's how I.
So he coined the term inertial induction, that if you succeed to get energy from space-time, this energy comes from someplace. So suppose that we have like an electrogravitational generator that generates electricity, and everyone is happy because you get a lot of electricity. You get like, let's say 1 megawatts out of it, and you don't pay it. You actually do pay, because because of your device, the moon will lose energy and approach the Earth, or if the Earth will lose energy in relation to the sun and approach the sun, because it lost gravitational energy, then your device is destructive. It will cause much more harm than
What about
any
Maxwell's-
fossil
There's
fuel.
lots of examples where gravitational energy uses, like hydropower. It's not destructive. It just uses gravity to produce electricity by the flow of water.
This
through
is
a
not
turbine.
destructive. Yeah, this is not a destructive form. But we
That's
talk
not really
about,
using gravity. That's using the sun power. That's solar power, really.
that's also not destructive.
Well,
But if-
solar power isn't gravity though. It's electromagnetism. It's what Einstein got his Nobel Prize for in 1909.
The truth is, everything that's here except for nuclear is solar power. Because how'd the water get up to the top of the mountain? Because the sun heated up the
Evaporate.
ocean, and so the energy came from the sun.
Or you pumped it up there.
Well, it pumped it up there, right? So that's where the energy came from. But ultimately, what we really need for free energy and what will solve the energy crisis is Maxwell's demon. If we can find a way to convert direct heat into energy, meaning that you turn on your air conditioner in the summer.
Oh, I can tell you
Instead
how
of-
to do
instead
that.
of
It's
costing
interesting.
energy,
Three-phase circuit
and instead
through
of
a vacuum tube.
instead of costing energy, it actually produces energy. If you can do that, then you've solved the energy crisis.
Hey,
What about
Bernie,
the Stirling engine?
you're muted, by the way, Bernie.
Yeah, Bernie, I think you hit the.
Instruction about using a vacuum tube on how to do it.
Vacuum tube, 3-phase, and the third wire is a mesh through the middle of the vacuum tube. It's an 1950s or 1960s Air Force video, educational video. It's about 5 minutes long, and it
Can you find it?
They directly state you will take heat energy and turn it into electricity with a vacuum tube, anode, cathode, and in the middle is a mesh, and it turns it into a third
Oh.
three-phase.
Can you send a link? Can you-
Yeah, we would like to see a link of this. Can
Well,
you
well,
find it?
guys, if I could jump in also, what Mark, what you're talking about with Maxwell's demon, and this isn't against Bernie at all, but I just read, well, about a year ago now, they did that experiment, and this was how to draw energy out of heat energy using Maxwell's demon. It was the exact same thing. This was the one, you probably remember it, I told you about it, where, okay, in the 1950s, some scientists proved that you couldn't use a rectifying diode to do this in a circuit he did some complex mathematical proof. And so everybody gave up. They said, we're not even going to try it because it's been proved to be impossible, right?
They did it with 2 diodes.
They
Yeah.
do, yeah. So there you go. That's your circuit, man. That's the basis for it. Now, what Bernie mentioned may also work. That may be a mechanical way to do it or tube way to do it, but there's a proof that it can be done.
For diodes too, but the issue is perfecting it. It's not. It exists. It is possible, but
I'm gonna try to find the video right now. It might be Bell Labs or just straight U.S. Air Force, but
there are ways to convert heat into energy, but it needs to be above ambient temperature, or it needs
That's true.
temperature
it
gradient.
depends on the gas you use in the vacuum tube for what temperature it pulls energy out of.
Mhm.
Can
What
it
about
pull it-
Peltier? Mark, what about Peltier element?
What element?
Peltier. It's you have like
Peltier's pumping
thermoelectric coupler.
Yeah.
The Peltier's pump.
Solid state heat pump.
Yeah,
Oh,
heat
solid
pump,
state heat pump. I mean, those don't. They don't really cool down enough. in
You
order
have
to-
a thermal.
No, but if you use one side
thermoelectric
is hot
too.
and the other is cold, you have one hot
Yeah,
side
you need
and
a
not-
gradient, but it's not Maxwell's demon though, because
Mhm.
it requires the gradient to produce electricity, right?
Right.
So what Mark is saying is you can
Come
just
on,
put it in a
Maxwell's
room. And,
demon, when you go from a gaseous state to a liquid state, you're decreasing entropy. When you go
Right.
from a liquid state to a solid state, you're decreasing entropy. So don't act like it's something special. It's just a change in state. It's a medium change.
Think of all the
The
energy. that enters your
space-time
house.
is different. The space-time is different in a crystal than it is in a liquid.
That's
Think of
true.
all the energy that enters your house as electricity, taking in 10 kilowatts. All of that energy comes out of your house as heat. We need to just reverse the cycle and take all that heat and put it back into electricity.
But there is another invention. It's called the Stirling engine.
Yeah, I've seen those. Those use a gradient too.
Oh, okay.
yeah,
all-
yeah.
Well,
They, you know,
I
they
think you're
use
on the
those in,
right track. Like, for example, a thundercloud has how many megaton nuclear warheads would it take? It's like hundreds of megatons of
I
energy.
found
In
it.
one storm?
And
Oh.
one simple thunderstorm would be in, like something like 250 megatons or something like
You don't
that.
even have to do that. You
So
can
how
just
come we
suck
don't
the
store
water
this
out of the
energy?
ocean and cool it off.
Two people I couldn't hear.
You suck water out of the ocean and cool it off, both cooling off the planet and producing electricity.
That's right. Or suck water out of the glacier and put the.
Or just take some water and run it. Take water and you run it over something, it cools it down. It's just by running water.
Can
in
I
electricity.
share screen to share this video?
Yeah.
Go for it.
says host
Sure,
has
the
turned
link.
off share screen.
1 second. Can you share the link too?
I've already posted it in the chat.
Okay, try sharing the screen now.
No, still not letting me.
Try now.
There we go.
The controls must have changed when I,
There you go.
oh, look at that. It is 1950s. Electronics
Prepare to
at
have
work.
your mind blown.
Good luck to see if you got sound with that. Nope.
Oh, it's not doing sound?
Well, it's playing sound through your mic, I think.
Hear it?
Yeah, you gotta keep making noise on your end then for it to-
Oh, okay. What if I, can someone else play it and it'll play the sound?
Mark has it set up to play sound.
It's not gonna be much different than this.
Contacts are insulated from each other by a vacuum or by some inert gas inserted into an evacuated tube under low pressure.
This is not a.
I can play sound if you want.
All we need to do is heat the cathode.
Yeah, that's just a.
I can.
Okay, that's the thing.
And here's what happens. As electrons are emitted from the surface of the heated cathode, being negatively charged, they fly at tremendous speed to the anode. This way, a current carrying path is formed, which closes our electronic switch and permits our motor to operate. You'll notice, by the way, that the direction of electron flow is contrary to the orthodox concept of current flow from plus to minus.
So I have to talk for you to hear it?
No, it's doing okay.
Okay, very good.
We can do this merely by connecting an electronic tube in series with an AC circuit. As you study this circuit diagram, note that only each positive half wave of AC voltage will now produce a current.
Okay, so that's like a diode or?
Yeah, it's a diode. It's a what's called a Schottky diode.
In other words, because only the cathode can emit electrons, we have here what amounts to a one-way stream.
AKA a vacuum rectifier.
Result of the tube
Mhm.
electrifying
So what is this?
the aid of these two oscilloscopes.
How is this
Okay.
a heat
It
source?
starts at 3 minutes of the relevant part.
Okay.
The one on the right shows pulsating direct current going out. The applications of this basic rectifying principle are many and important. The second basic thing we can do with it is amplify. Here's how. Between the cathode and the anode of the two-element cube,
This is like movie night, huh?
we now
Movie
place
night at APEC.
Yeah.
to this grid, we connect an input of some weak voltage which we wish to amplify, perhaps that of a faint radio signal from halfway around the world. Now let's see what happens. Every time a negative potential is impressed on the grid, even though it be very minute, it has a large effect in reducing the number of the negatively charged electrons which would otherwise keep flying from cathode to anode. Conversely, when the grid is positive, an equally large effect is exerted in increasing the flow of electrons from cathode to anode. The important thing to note here is this. A small amount of power applied to the grid is amplified into a large amount of power in the anode or work circuit. This amplifying property of the three-element electronic cube is put to work in innumerable ways.
Yeah, but that's
Okay,
a normal
can I,
amplifier.
Yeah, can I
That's
take
cool.
a second to explain to you what that is and what that's doing? It's not making power. What you're effectively doing
The
is
the original clip was 5.5 minutes long, and it totally did not play the part where it talks about that. Weird.
is it just a similar triode like that though?
No, it's the exact same video, just there was parts edited out.
That's weird. Really?
Was it ever replicated? You said you get more energy.
Yeah, you have the antenna attached to the wire grid in the middle with it, and it amplifies from the heat. It cut out the part that explains that.
Wow. Yeah, that's kind of the key part, huh? Funny they cut that.
I've never heard of such effect before. No.
So when you forward bias a diode, that's where you get your amplification. And you do that, but it has to have some sort of gate, and that's what that was why it's a triode. You apply bias to the gate, and so it's kind of like what's called a MOSFET, only instead of an O, it's using the vacuum.
Really much more like a transistor because it requires a continuous current flow to be sourced to that thing in order to either increase the current flow from the cathode towards the anode.
I see. I got you.
Yeah, but you're wasting energy powering the tube in order to get that extra energy. It's not pulling the amplification power from anywhere.
It's pulling the power from the atmosphere with the antenna.
Yeah, that sounds right.
Oh.
Yeah.
Or from the microwave
Well,
background radiation.
the atmosphere is not cooling off because of that. It's taking small, minute amounts of radio energy that's already there.
Yeah.
So, and that's what metal does anyways. The antenna does that on its own.
That's true.
But then it's the vacuum tube grid that amplifies it.
No, it's the power that powers the vacuum tube grid that amplifies it. The tube grid just lets you amplify it precisely at that frequency.
Yeah. Basically, we'll put it this way. If you don't supply a positive potential to the anode and have some current behind that potential going to the anode, it doesn't matter what kind of signal you put into the grid, your tube's not going to generate an output.
Exactly.
You have to give it the power. Otherwise
Bernie, what we're talking about is a device that if you put it in the room and started sucking power, like if it started sucking power, it will cool off the room.
Yeah, isn't that essentially like a ground and then the antenna and then
No.
That sounds cool.
No,
the ground is pulling energy out of
No pun intended.
the earth?
it would be cool if it worked, but there is no such thing. There is no such thing at the moment. Now, if there was, it would be it would win all the awards and solve the world's energy crisis.
For sure, yeah.
Although there is that the two diode system. I know the voltage output from it was very low, but nobody's pursuing that, and that's a real shame, because that's something that can actually be be perfected, and if they can make like maybe large sheets of diodes or something like that working together, could cool stuff off, and you could use seawater or something like that with heat pumps, and you can maybe actually both cool off the world, from global warming, and create energy at the same time.
One thing is for sure, Mark, is that let's leave the tube alone. If you create an inertial dipole that is strong enough, then you get a spaceship that flies up, and then you say, okay, let's drop it down and get the energy. So you can elevate it, and then you drop it down, you elevate, and you will get more energy than the energy that you need to drive the charge into that spaceship, but it comes on the expense of far bodies of mass. So after a while of using this energy,
if you do that on what time would you have to do it? You have to do it on the time of Earth when you're facing away from the sun, meaning midnight. Then you'd be able to pull the Earth farther away from the sun.
That's true. That's 100% true. That's one of the things that should be said, and you said it. That's true.
Yes, and then you'd be able to fix global warming another way.
But maybe you'll pull in like a far asteroid, so we don't know exactly what it will do.
Well, if we have that technology, we'll find the asteroid and we'll
and divert it. That's also true. Could be true.
Yeah.
So, but that's the idea. This is an example of why using warp drive to generate energy has its risks. It will cause some troubles, some problems that we'll have to fix. But there is another theory that says that energy is not conserved in general relativity, and you can find it also in Wikipedia. Energy is not conserved in general relativity. Why? Because there is like this term that it's called the cosmic constant. So you get like an accelerated expansion of the universe, and you can be a leech on that. And by using the Mach principle in a way that energy will never be depleted. So that's another way to think that maybe using warp drive to generate energy is not so destructive. You won't do it when you're aligned with the moon, that's for sure, or with the sun.
So Eytan, you should look into Alzaphon, because it's a very interesting theory, and it basically goes. He looks at gravity as a direct interaction between particles, but he states one thing that's important to notice is that the subatomic particles are the source of gravity. That's the source of inertial mass, which is the source of gravity. And we know that the core of the atom, the particles are chaotic. They're completely random spins and all that. So if we were to orient the spins of a spacecraft so that all of them are of the same plane, the plane and axes of their spins, then they would no longer be able to interact with the spins of the on the planet, because the spins of the subatomic particles are all random, and they would try to interact with the craft, and essentially the gravitic connection would be cooled by that interaction, and the craft would become weightless.
Well, I'm not very fond of particles. My view of the world is that the basic components of physics should be events and not particles, and that particles should emerge as misalignment in these events. This is more like
them as particles either. He sees them as waves that have very sharp points that go off into infinity. So he sees a proton as both a singularity and the entire universe.
Yeah, but it's still it's one version of the quantum particle. Yeah, but think about it that you don't have particles at all as building blocks. You have only these causal sets that you call chronons. And this is a very different approach to physics. They say that your building blocks are no longer particles, but are just events. And when these events are misaligned, you get particles. By the way, it's a result of a theorem by Rib that he said that his field has a zero rotor. That means it has other sources or drains. And this is exactly what particles mean. And if you consider a Rib field which is complex, then you can also get something that the real part of that field is zero. That means zero charge. The real part of the divergence, I'm sorry. So you can get like zero charge too from it. So this is a different way to see nature via particle, not via events, not via particles. It's very different.
Yeah, I mean, there's a lot of different theories out there. What I'm more interested in is who has something that I can try in a lab that will prove results one way or another, and that's why I went with Alzafan. I mean, here's the Podklanov paper, and he makes all his claims, and Alzafan wrote his paper in 1981, and there's more papers here than there are experiments, and that's the problem. And there's more theories than there are papers. And every single experimentalist, there's probably 100 theorists for every experimentalist, and every experimentalist is a theorist also.
Probably we should get on our meetings, we should get people from H4D from Brazil. Try to contact Elio Battista Porcelli.
Oh, okay, that's a long name. Can you write that in the chat?
Yeah, that. Go to research gate, Elio Battista Porcelli, or Victor Filho. I'm not sure about the spelling of the last one. The first one is correct. The first name. They're from H4D. In Brazil.
What does he do?
He does the experiments with inertial dipoles. So this is extremely important, especially for these meetings.
Oh, cool. Yeah, we could definitely get this guy on. Elio Battista Porcelli, service manager at Yamaha Music?
No, he's from H4D, Brazil. And look for it, H4D, Brazil. Just look for H4D Brazil, and you can write them an email.
Yeah, it is. Yeah, he works at H4D. He's also a service manager at Yamaha Music.
I didn't know that. I didn't know that's the same guy. I'm sorry, because I didn't know. He has a master's degree in physics.
Yeah. This is, yeah.
So I didn't know that's the guy.
Yeah. H4D as well. He's he's a researcher on the side, and he makes his money as a service manager for Yamaha Music. Same guy.
That's a shame. That's a huge shame. I didn't even know that it's that bad. Let's see if we can do that.
Eytan, what do you do for a living?
Now, I think we should write to him and tell him to join these meetings. Here's what you can get from from ResearchGate.
Oh, I tried to connect with him on LinkedIn.
That's another way.
Yeah,
but he must be and make sure that Tim Ventura succeeds to contact him.
Yeah, Tim Ventura, he seems to know a lot of these people. I refurbish hybrid batteries for a living and do the anti-gravity on the side. Nobody here does this for a living. It's there's no money to be made until we make a discovery, at which point it will be the biggest industry in the world.
That's true. That's true, but it's a shame that mainstream is unable to listen. I tried to publish a paper, this paper in Foundations of Physics. They insisted on an experiment. They said they write it explicitly. They say we will publish if you give us A corroboration, experimental corroboration. That's the theory alone is not enough. They want to see corroboration.
Well, if I had an experiment working, I wouldn't need to. I wouldn't need you to publish. It would
That's
be
true.
on CNN. It would be on Fox News.
Yeah.
So what kind of experiment?
You'd be
did you want
begging
to
me. Like,
do? What kind of experiment did you want to do?
It's enough to show that electric dipole without opposing dipoles in the middle will generate a repeatable thrust. That's it. That's sufficient, and it has to work in vacuum too.
And what do you need to do that?
Well, to repeat that, more people will repeat the experiment that Elio Battista Porcelli performed, and to do it correctly, not to do it with a very high dielectric constant, because when you have a high dielectric constant, you get dipoles which are counter-aligned and destroy the effect. So we need to have a sufficiently large charge density on the plates on one hand, and on the other, we don't want to have oppositely aligned dipoles in the middle.
And what kind of equipment setup do you need?
Well, you ask me something that I'm not sure. That we need something that can resist very high voltage. That means the breakdown voltage will be as high as possible, and that the electric constant will be as low as possible, as close as possible to 1. This is the material, and it has to be heavy, because this part of insulator slab, that's the mass that will be accelerated by this inertial dipole. Because what is said, but Chronon field theory, what it says is that electric dipole generates an inertial dipole, but the measurement is very like the prediction. So the prediction predicts a very low effect that is very difficult to measure.
So have you already determined what material that is?
I don't know what he used. I don't exactly. I think he writes it down. I don't know. I don't know what's the best material. I know the Teflon is good. Teflon has a high breakdown voltage, and it has a relatively low dielectric constant, probably something close to 2. But then you have a problem. Then when it is too thin, then it will not survive, like for say 100,000 volt. It will break down. If it's like let's say 1/10 of a millimeter, doubtfully it will succeed to withstand 100 kilovolts. Yeah. Now tantalum pentoxide Ta2O5 has a dielectric constant of 25, which is not good, not so good, but it can withstand a very high voltage. So maybe with the high enough voltage, we can compensate for these counter-aligned dipoles in the middle. I have a calculation.
Let me ask you real quick, Eytan, the experiment that you wanted to see people replicate more of by Porcelli is the new evidences of anomalous forces involving high voltage symmetric capacitors.
Yeah, shielded. The shielded one.
Right, the shielded one. And in that experiment, it looks like he uses acrylic sheet as his material, 2 millimeters thick, at up to, I think in the charts it's 20,000 volts. His multiplier goes up to 40,000.
Used 40,000 at most. If you look at the paper, you read the paper, you will see that he used 40,000.
The paper says he uses a 40,000 volt multiplier, but the chart only shows him charting points up to 20.
Only,
why I was saying
so he used only 20 first, so I didn't read it correctly.
So anyways, we've tested that same configuration with exactly the same material from what he lists, PMMA, which is basically just acrylic. That's the name.
What is the relative dielectric constant?
Of acrylic? It's really low. It's like in the single digits.
Think how much? Like 100 or 20?
Oh, no, like 4 or 5.
That's good. 4 or 5 is good. But how much charge can you accumulate on the plates? What is the distance between the
Well, I
plates?
can tell you that at 2 millimeters thickness, we can get at least 120,000 volts across it.
Okay, so what is that charge density you get for 1 centimeter? Because what happens, the effect is, it depends on the charge density divided by the electric constant.
Well, I'm not sure because the PMMA that
problem
they
is-
use is going to determine the charge density, right? Because this dielectric constant is going to control how many charges we can get onto the, from the plates into the surface of the dielectric. And so it's going
also
to
not
ultimately be
linear.
the same for if we use the same materials and the same size plates, we should have an identical experiment at the same voltage. It's pretty much,
Can you-
conditions
yeah.
are
Can you
I just-
accumulate? I'm sorry.
I
Yeah.
just put, sorry, I just put the PMMA link for the dielectric constant for PMMA in a paper.
awesome. Yes, you did. Check that out. Okay, let me just read that off. So not
Something that's
everybody-
important to note is
No, I
that
don't get it.
many of these
Redirect.
dielectric constants change. Like if you get the voltages per mil and you try to times it by 10, the voltage that you can withstand is not necessarily going to be times 10. It'll probably be times 5 or 4. It's an unlinear scale going up, and once you get past a certain thickness, like the electrons can pass around the object too.
Can you get 10 to the power of minus 4 coulombs per centimeter square?
I am not sure.
That's what we need in order to get at least with the electric constant of 20. That's what we need in order to get a measurable result within the 0.1 milli 25. The electric constant is, let's see if it's 25, and we have 10 to the power of minus 4, and you have a slab with 8.2 or 8 grams per cubic centimeters, then we'll get a measurable result.
And by the way, PMMA is a dielectric constant of 4.9 at 100 hertz. So just to kind of give you an idea of what they used in that experiment, it's not particularly high.
So what is
I think you're looking at something more like graphene or silver. Sorry, graphene.
Eytan, what if you put just one atom layer thick or one molecule layer thick of a high dielectric constant material?
The electric constant will destroy the effect.
No, but if it's only one molecule thick,
it will still block. It will still this is the layer in the middle is the layer that is accelerated by the effect. So it's shielded. So I'm not sure it will be shielded.
Yeah, but you're saying 10 to the minus 4, so.
We don't want it to be shielded.
well, what if the layer in the middle had high dielectric constant and was just one molecule thick?
It will actually counteract the external dipole. Because if it's minus below and plus above, it will be the opposite. It will
So are
align
you
opposite.
saying basically we just need the highest mass possible, highest voltage possible, lowest K possible dielectric. So effectively what we want,
Right.
solid dielectric that acts exactly like vacuum.
As close to vacuum as possible.
Okay, that simple definition makes everything real clear about what we're supposed to be going for here.
Sure, just use a vacuum.
If we could pull it, if we could
No,
pull
but
down
vacuum,
that far,
but vacuum will break. I mean, electrons will live through vacuum.
And in the market, there's lots of vacuum.
There's another problem. Sorry, vacuum doesn't weigh so much. We need mass. We need this slab to be as heavy as possible, as
How
heavy
about-
as possible.
How about something like
But
glass,
vacuum does have.
like a Leyden jar?
A Leyden jar. Oh, yeah, I forgot about that one. Yeah.
Any material that can be both heavy with a low dielectric constant with high breakdown voltage will be good in the middle. And we should have like the highest possible charge density on the plates. Then we can succeed when we will generate an effect
then
that
if
is
you get-
measurable.
If you get 4 Leyden jars, you can basically create harmonics, make it oscillate.
Well, I've mentioned it here before too, as far as low K, really high voltage, dielectrics, but polypropylene I have some polypropylene that is, and I think I measured it 0.02 millimeters thick. Is that how thick it was? And it can take 50,000
That's
volts.
good. That's good. If it's below 0.01 millimeters, because with the tantalum pentoxide, it's something like 0.01 millimeters for 1,000 path.
Yeah. Anyways, this stuff you can get like 200 kV per millimeter. So
Yeah,
in terms of voltage isolation,
preamp.
it's really high up there.
Actually, search for, go to 3amp.com and they'll have a complete list of all that. With all the values.
So with the tantalum pentoxide and 1,000 path with plates of 1 square centimeter, the distance is 0.2213 multiply that's multiply 10 to the power of minus 2 centimeters. So it's actually 2.213 multiply 10 to the minus of 10 to the power of minus 4 meters. Right? It is. No, it is. It's less. It's 0.20. It's 0.2213 multiplied to the 10 of minus 4 meters. So it's 2.213 multiply 10 to the power of minus 5 meters. That's the distance that you get with tantalum pentoxide.
So my question about this experiment, ultimately, I wanted to come down to this. When we tested acrylic capacitors at very high voltages, much higher than what he used, we didn't get any kind of a force whatsoever.
So depends on how much charge do you have, how much charge density you have. I can give you the formula. You know what? And
Okay,
then
no, I mean, this is what I'm saying. Okay, if he used the same material that we use and he used the same size plates that we use, then the thing that determines the charge density is the plate size and the material and the voltage.
And the node. Also, if whether you have an AC component or not, because if you have an AC component in the voltage, even a very low power.
Now, here's the thing, though. He didn't have an AC component in his voltage because he used
He wrote to me.
Has a DC smoothing factor to it just because it's a capacitor parallel to the output.
Yeah, but it did have. It was a low, relatively to the voltage. I think it was something like 120 volts ripple, but he had a ripple. For sure, he had a ripple.
Yeah, because I looked in that and it wasn't listed in his equipment used. Anything
That's true.
Ripple.
That's true, but he wrote to me that he did have a ripple.
Well, if it's not in his paper, though, that's not going to really help us if we read it, though, huh?
Maybe he can send you what he wrote to me.
That would be very helpful. Now, that would be very helpful. Indeed. Let's see. I see volts, amps. That's his meter. Yeah, in his schematic diagram, he shows what looks like a variable battery and a capacitor. So variable voltage source and a capacitor. He's not showing any kind of ripple at all in his schematic for this thing. It's just a straight up DC charge, and we've tested straight up DC
No,
charge.
he did. He said that it's negligible. He emphasized that it's negligible, but it's not negligible. So that's totally untrue. I disagreed with him on that it's negligible, because this is exactly what is needed to create a further effect, which is called the White effect, the Hurd-White effect. So I did not agree with him on that. I'm just looking for it.
Trying to figure out where this is, the frequency that he's putting in here.
Yeah, hopefully that.
Let me just type in. I'll just do a search for Hertz, HC, and let's see. Yeah, nothing.
No, just I need to get the letter that you wrote to me. That's need to do login. You know what? I have to log in and give you this. That's otherwise it will not work.
Okay, so let's see the variation. The dielectric constant, the frequency increases as reported in the case of TiO2.
It didn't. Okay.
Interesting. Is he saying that the K factor actually goes up when you introduce AC?
No, I don't think so. That's not what he wrote to me. He wrote to me that he didn't even talk about that. He talked to me only about the AC component, that he said that it's negligible and shouldn't introduce any effect. And I totally disagreed with him on that. I said that even a weak AC has an influence. Oh,
he's claiming huge weight changes here and even a calculation to go along with them. which I don't know where that came from, but I mean, these are just massive amounts of weight change. And considering that we got 0.00 nothing at like I said, at already 80 kV we tested it at, I've had
Okay.
voltages as high as 130 on those things.
I'll put it in the chat because we talked about where it is. I'm not very happy to do that, but this is the chat with him, but I don't know if I should do that because he didn't tell me that I'm allowed to share it with anybody.
Well, let's at this point just make sure nobody shares the chat. You know, we should not post this publicly. In fact, I don't know if you can delete it, but anyone that wants to see that, I guess see it now. I don't know if you can delete it yourself or not, but
no, you will see it out of the video.
Hey guys, you know, actually, if I could jump in real quick too, if you guys could help me, I need to do write-ups for the stuff you guys are discussing. Obviously not, you know, not this, but I mean, for this conference session. And so for like, for Eytan stuff, I need to try and figure out what the summary would be. But then I know there are other parts that I've missed, and I don't know.
Honestly, it wasn't really like an organized presentation. I think we should have Eytan back to actually like do it, you know, start to finish.
Yeah,
Maybe we'll have a Sunday session or something like that, or
Yeah,
That will be. I wish my wife was on that because she's an active part of the invention.
Eytan, I have a question for you.
Yes.
How can you be a religious Jew and, you know, believe in this stuff and, you know, anti-gravity and all that?
Why not? I don't
Because-
put. Nobody will put
Connect
from
to
me.
source. It's like you just know.
Yes, because like as soon as we have the technology to split the sea and create carbohydrates by removing the carbon from the atmosphere, and then basically that's what happened in the Torah. It's a story of it's a story of a warp drive and advanced technology. I mean, why did he tell Moshe to take off his shoes so he would be grounded to protect him from the ship? It's obviously it's talking about extraterrestrials. It's not talking about God.
No, it does. Yeah, that's an explanation which is very convenient to us. On the other hand, nobody will say that there are no extraterrestrials because then anyone who says that puts handcuffs on God's hands. That doesn't make any sense.
Well, it doesn't say God in the Torah once.
Well, you know, if I could jump in, I think it's intriguing that so many scientific great minds are also deep, you know, men of deep faith, women of deep faith, people of deep faith. Maybe we'll put it like that. You know, so, you know, I mean, now I'm not saying anything about any one particular religion, but maybe it's like that old saying, it doesn't matter what you believe, it matters that you believe, you know? And I don't know. I just think it is interesting though, that so many great scientists have been very openly people of faith.
That's true. Even Isaac
Yeah,
Newton, yeah.
I totally agree with my Jewish colleague here.
Guys, how I can explain that is once you grasp the overall structure of how it works, there's just no other rational way other than some sort of consciousness or intelligence structured and built it all, and that it's greater than you, and
It is you.
right. So it's like
It is you. If
exactly.
If the energy is infinite, then I can't not be it.
Right.
also.
Well, one of my favorite sayings is I come up with is I am God, but so are you, because energy cannot be created or destroyed. The soul is immortal. It's just phased from one phase to another.
Right. But the Torah doesn't talk about God. It talks about Jehovah. And
But also talks about the tetragrammaton.
that's Jehovah. He was a
and the whole Hebrew language is structured mathematically, and that the cymatics are the perfect waveforms that come out, like that each sound actually is a full frequency sciatic frequency.
You're trying to sound like my dad now.
Sound in the Jewish language. That's why it was one of the purest languages, and Sanskrit also was like that, where if you say the sound of each letter properly in its tone,
I get that.
cymatic frequency, it will produce a it comes out as a complete one each time, sort of
Okay,
thing.
Bernie, do you know the Bible? Have you learned the Bible? There's a story.
I've not read the Bible, but
Okay, there's a story in there of the sea splitting and the Jews walked through it and the Egyptians followed after them.
aware of
That was
it,
the big revelation that happened that convinced everyone that this thing is special and we should worship him therefore. But I'm saying, like, if we come to the level of technology where we can do that to primitive cultures ourselves, we can travel interstellar, we could split the sea and we could free the slaves and do all that. Who's to say it didn't happen here, and that the people, the beings, the entities that we're worshiping aren't extraterrestrials? They are.
You can't say that because you haven't been
I
there.
believe that
I can't say that because it's history. I can't
goes in
say.
ages and cycles, and that at some point we are a much higher dimensional or consciousness or technically advanced species.
Who's to say
And then
plants
go up
don't
and
have
down.
consciousness?
I believe in catastrophe.
Well, if we have the technology at someday to do this to another civilization, where we could basically replicate all of the miracles of the Bible through advanced technology, like think of the Shamir, the
Yeah, it's
Shlomo
something.
Melech went looking around for this Shamir, this special
Stone.
No, it wasn't a stone. It was apparently a like a snake or a worm that can cut stone. What does Shamir sound like? Shimmer. It's a laser.
So
Could be, but we haven't been there. I don't know.
It could have been a worm too.
Well, that's what they called it a worm, but it was probably just a laser, because that's what makes sense. We're looking at modern technology. What can cut without metal? A laser can.
Or a drill. It could have been a drill.
No.
Apparently a worm can.
It specifically states that it was able to cut stone without the use of metal, and it was called the Shamir.
Oh, I don't know. I was raised Christian. We were taught not to question things. So.
Hey, wait.
I'm just messing
You know
with you.
that's not true.
But I don't want to get us kicked off YouTube either, you know. So
there you
We're
go.
not on YouTube anymore.
So I think God's a she, not a he.
Well, that
Beyond she and beyond he.
Yeah, Tim. Let's face it, Tim. At this point, I'd say we cut everything from a little bit prior to this when we get the religion stuff all off of this for YouTube, and then anybody can just say whatever the hell they want. So let's kill recording actually at this point.
Why I want to say that there is a
actually just leave it on, but cut it out. Let's leave it on just in case somebody says something like truly revolutionary and amazing that we have to go back and look at. That one little tidbit that Eytan like spouts out by accident, or maybe Esoteric has some monoatomic go crazy on him on camera.
We've had our share of moments. We had that time. In fact, right, the reason I have the camera off is my wife is on the treadmill in the back room, so she's like, turn the camera off. But then we had the time that I think Jeremy was smoking out on camera, and it was on gallery view, and he thought nobody would notice. And I'm like, is he lighting a bong? And he's just like, and he did this enormous exhale, right? And it was really obvious. And I'm just like, you can't get
Did
high
he have
like
the
that.
sound on too?
No, he didn't. He thought
That would be perfect.
he thought he was being sneaky, right? And I'm just like, you can't do that. We're recording. So
One of the times Jeremy fell asleep during the live stream, we had to like wake him up.
Ron, right, when Ron falls asleep, and I do feel bad, right? Because our sessions, even if we say we're going to do 2 hours, it ends up being 6 to 8. And so Ron would be in there, and it'd be like 4 hours in, and Ron would be like snoring, and his head would be bobbing, and be like, okay, nobody talk loud,
Yeah, well, that's one thing I worry about.
The legend needs his sleep.
One last word for Jeremy. This is why in most cases you don't see a thrust at all. Look at the formula. You get the acceleration, the gravitational acceleration in capacitors. You'll multiply this value by the weight of the slab that you use in the capacitors, and this is the force this is actually the force that is exerted on the slab. Now you can do something else. You can take that acceleration and subtract it from G, and you will get how much weight is lost. And you will see that it's so small that in most cases it's not even measurable.
But if we add if we add a symmetrical AC component on top of the DC bias, is that going to, do we automatically enter the genre of generating a unidirectional?
Then no, then you change the experiment. Then you cause also a Harold-White effect. But I don't think that that's the reason why you were not able to measure anything. I think the reason is that you didn't take into account all the factors here. You have Q divided by A, which is the charge density. If the charge density is too low, then the acceleration is too low. So it's so low in relation to G that you won't get anything that you can measure. And then you take into account what is the weight of the slab, and you multiply it by this factor divided by G, so you can get the weight loss. So what you do A divided by G, which is 9.81, right? So eventually, if you want to see how much weight is lost, then you take A and you divide it by 9.981, and all this is multiplied by the mass of the slab. So it can be so low that it's not even measurable. And that's the problem with most such experiments. You depend on the charge density.
This is what I want to know. And you read this experiment, the one that you specifically recommended you wanted people to replicate. I mean, you're familiar with this one then. What are they doing to get charge density high enough to get insanely high results, which they're reporting here, huge numbers? These are highly measurable numbers.
Then you need a thin slab, because if you get a thin slab, then the charge density is going to be higher because the capacitance will be higher. So, but there is another effect, because if you have the slab is too thin, then it loses mass. Then it not loses mass. It's the mass. It's not very high, and this is the mass that is multiplied by A. So you need like to take the mass, multiply it by A, and divide by G, which is 9.9, which is 9.81. So you need a heavy slab, but thin enough. And I don't know what to say more than that, Jeremy.
Well, I guess I'm just gonna go ahead and like literally replicate the experiment down to the 69 millimeter wide plate area, and then I'm going to test it inside of, well, I'll test it outside of a shield first to see if it does anything, because if it doesn't do anything outside of a shield, I wouldn't expect it to do anything inside of a shield.
And take into account the formula. You have an exact formula also.
Jeremiah, can you post a link to that, to the patent that you were talking about?
The patent, I still haven't been able to find it, but I'm just looking at this other paper that he referenced.
Can you post a link?
I was hoping that he could post a link to his own patent, because he would know where to find it.
Quantification.
Oh, so this is something that you have on your computer that's not on the internet, right?
No, I found it on the internet, but the one that I found was it was like a web page that was trying to display it from another page that probably hosted it and just didn't show up right, so I didn't bother to try to link it.
You know,
I have no idea where it is now. So
I just found that PMMA is available now as a filament. So you could probably, if you need a really thin filament that's more precise, probably you can 3D print that. Very thin, just a single layer.
well, PMMA and acrylic, they are the same thing, right?
Not chemically, no.
Not all right, because when I looked up what PMMA is, it says that it's the name for acrylic.
It may be a type, but it's not the same chemical makeup.
Is PMMA opaque? Is it like whitish or is it clear? Because
Well, it's usually clear because we use, my lab doesn't use PMMA, but other labs which I collaborate with, they use clear PMMA.
And so plexiglass, for example, like that would be an example of PMMA?
No, it's a very different thing. They usually use PMMA as a liquid. and then to make flow systems, inside the PMMA. So PMMA has many different forms. But I think chemically, I don't think chemically is the same. It might be.
I'm looking it up on
It might share some
No, write it
common,
again.
some common root, but I don't think it's exactly acrylic.
Yeah, I think, I mean, I see what you mean, but yeah, it does look like acrylic is literally just the brand name for, or the material name for this stuff. Because I'm looking on a website that talks about the variations of it, and every single one is labeled as a variation of acrylic and PMMA both. So
Right. So same root, right? So, but probably some sleight of hand.
I mean, it appears. Well, let me look it up. I'll look it up real quick. I'll look up the chemical formula for acrylic.
I've never heard of liquid acrylic. So.
Well, so you ever heard of superglue?
Superglue, sure.
Cyanoacrylate.
It's a cyanide.
Same material.
It's a cyclocyanate, yes.
Yeah.
Is that acrylic, or it might be a variation?
You can buy a liquid form of acrylic to bond pieces of solid acrylic together as an adhesive at plastic
Yeah,
shops.
that's true. Yeah.
So it is available as a liquid.
Now that he left, what do you guys think of that guy? What's his name? Bernie.
Bernie is, well, he definitely partakes of a lot of things, and I don't think that he's ashamed of it. He has a kind of wild setup, and he's an alchemist, and he does what he wants. So he is to himself his own character, and by all means, he can do what he wants as long as he doesn't care about how it impacts his image. I mean, he's going to show people the side he wants them to see, and I don't care what side that is. It doesn't affect me.
Did he teach you anything?
No, Esoteric Gold is the guy that I'm going to be learning a lot from, but unfortunately, I don't know if I can get a constant enough train of thought or the memory to, really give my power to the other guy. But he's highly entertaining nonetheless. I have nothing against him whatsoever.
I had to shut him up quite a few times and mute him because he's just like, I couldn't get a word in. And he just like continues talking on top of like mute.
Yeah.
I see a finger doing something. I'm not sure.
That's Esoteric Gold, yeah. He looks like he's onto something there. He's got some nice light fixture. I don't know what's going on there.
Gotta have the candle. Gotta have the fire, man.
It's ambiance. I like ambiance. Ambiance is good.
Yeah.
Pinky. Pinky's having a nightmare. Eytan, have you ever seen the eye
I just
lifter?
looked up PMMA, and I'm looking it up right here. It is the exact same material. That's what it stands for. Polymethyl acrylate, which is where acrylic gets its name from. So it's literally the exact same thing. Yeah, that's
what was the thickness of your, let's say, what was the capacitance of your capacitor?
I actually never measured the capacitance of that capacitor.
So that is extremely important, because if you get a charge which is too low on the plates, you get a very low charge density, then you will get results which are virtually zero.
The same materials that they used, it should be impossible for me to get any other charge density other than what the material allows.
It depends on the thickness of what you use and also on the AC.
Exact thickness. Well, I mean, what other factors other than thickness and material and plate size could I possibly change that would drastically affect charge density?
Only the 150 volts ripple that you had, actually.
Right, which I can easily add. So other than that, like, there's nothing else that I had that was different, and my voltage multiplier would have had a ripple on it like that anyway. So it's just that in my test at much higher voltages, even with the ripple and without a ripple, because I did try it with an injected AC on top of it, it still did nothing.
Try to inject high frequency AC.
But like, I'm looking at the test setup, and they've got kind of like this hanging piece of metal pipe with Legos on it, and I'm not so sure that I'd necessarily.
And what was the voltage that you used? 100,000?
I can go up to 130,000, and I did try it at 130,000.
That's good. 150,000 is good. So now it depends on the capacitance. Very important to know what was the capacitance of your experiment and the ripple, the intensity of the ripple.
It would have been a ripple at what would it have been at? The fastest ripple I would have tested it would have been at 415 kilohertz, and it would have been a ripple of somewhere around 300 volts. And then the other one that I would have tested at, that would have been at the 130,000 volt range, and that would have had just a general leakage ripple of somewhere around 1,000 volts.
We'll try to use like
And that would
megahertz,
have
few
been around 24
megahertz. Yeah,
kilohertz.
I don't know what he did. I mean, everything can make a difference. Even
result.
like the material. What is the material of the plates? What is the connection between the plate? Everything can make a difference. In the...
Well, I will replicate everything that he's able to disclose in that paper that's in there up to the exact point that it's possible to do it. And I'll see it again, but I've replicated very similar papers like this, and I've gotten no results where they did get results. And I think the reasons for that were bad measurement, setups that I see the shielding, but I don't know if that shielding is grounded. I don't really know. If that shielding isn't grounded, if that becomes charged with a high voltage circuit or something like that, I mean, it would just.
I think I should put everything in one formula for you, so that it will be easy for you to just to measure the weight loss.